Today, we're going to look at finding the volume of a solid of revolution because I like spending an inordinate amount of time on this particular topic, partially because it's fun and partially because we want to put the analytic geometry, make sure we put the analytic geometry in our calculus with analytic geometry course. So remember, what we're doing is finding the volume of a solid formed by rotating a region about an axis. This is still falling in the category of our integration is multiplication in which one of the factors is variable. So in this case, we're finding volume by multiplying cross-sectional area multiplied by height. So we had two strategies for finding the volume of a solid formed by rotating a region about an axis. And we want to focus on just looking at the region and the slice without trying to draw the entire solid. So here were our two strategies. We had one where we slice perpendicular to the axis of rotation. So the example I keep using is this vertical axis of rotation. So our slice is horizontal and our delta variable is vertical. So what I mean when I say slice is here's the axis of rotation. We are slicing this direction. There were two cases where the axis is a boundary of the region. This is the case where we don't have to subtract off a circle in the middle. So this is a case where we are dealing with a disk. And the other case where the axis is not a boundary of the region. In this case, there's going to be a gap between the slice and the axis of rotation. So we refer to this as a washer. I used to refer to this as a compact disc because compact discs had the hole in the center of them, but no one uses compact discs anymore. So that brings the number of media that have come and gone in my lifetime to 2. So that's pretty cool. Actually, I'm not sure when cassette tapes, not like 8 tracks. 8 tracks predate me, but I think cassette tapes are post 71. I'm talking about the cassette tapes like you see in Guardians of the Galaxy. Like those were like mixed tapes. This is why we call them taping things. So, because it used to be on like literal tape, not sticky tape, but like a ribbon. So, what are we talking about? Oh, yes. Oh, cassette tapes do predate me. So, but I did record stuff on cassette tapes and now they're gone. I did record things on CDs and now they're gone. CDs did come around when I was around, so. What are we talking about? Ah, yes, discs and washers. So remember what we're doing here when we decide we are making a choice to slice perpendicular or slice. I spelled parallel wrong. I spelled parallel in such a way that it looks like perpendicular. We are making the choice to slice perpendicular to the axis of rotation, or we're slicing parallel to the axis of rotation. That's what we have to decide to do. So it's great that we have choices, but it's also awful that we have choices because now we have to make that choice. When in doubt, pick one and run with it. Once we make the decision, we have to identify if we're slicing perpendicular, we have to identify if the axis is a boundary or not a boundary. And that will tell us what our formula for the volume of the slice is going to look like and what we have to sort out with our analytic geometry. When we're slicing parallel to the axis of rotation, we don't have to, we're not concerned if the axis is a boundary or not. If the axis is a boundary, then R starts at 0. If the axis is not a boundary, then R doesn't start at 0. but we use the same starting place. So the volume of the slice was 2 pi times the radius times the height times delta x. This was a little bit of a manipulation of our area times height, in that we're looking at a cylindrical shell and we're unrolling it into a rectangular solid. So when we slice parallel to the axis of rotation, we're creating a cylindrical shell that we are unrolling into a rectangular solid. So we start with cylindrical shell that we unroll into a rectangular solid. So delta x is the thickness of the rectangular solid, and the 2 pi radius times the height is the area of a rectangle. So we're taking a cylinder with a radius and a height, and we're unrolling it into a rectangle with a height and a length, which is the circumference of the cylinder. So that's where things come from. Or we could ignore where things come from and just program ourselves with the volume of the slices, 2 pi times the radius times the height times the delta variable. In all these cases, we have to write, we always have to write in terms of the delta variable. So when we slice perpendicular, we have to write the radii in terms of y. This is going to require us to appeal to the function to turn our horizontal quantity into a vertical quantity, or write our horizontal quantity in terms of the vertical variable. The same thing happens when we slice parallel to the axis of rotation. We have in the picture that I've drawn, there's a horizontal variable, delta x. R is already going to be in terms of x, but h is going to have to be written is vertical, and so that's going to have to be written in terms of x. So let's do some more examples. Today I'm going to pick an example that's going to be difficult to use one style of slicing over the, so we're definitely one is going to be better. So let's take a look at a region. Let's look at a region what do I want? Let's look at a region bounded by 6x minus x squared and the x-axis. And let's find the volume of the solid by rotating this around the line. How about x equals -1? So we're looking at a parabola. Let's draw a picture of our region. Missed a little bit there. All right, so here's the graph of 6x minus x squared. We'll have intercepts at, x-intercepts at 0 and at 6. And we're going to rotate this about the line x equals -1. All right, so let's start by making a vertical slice. And then we'll do the problem again by making a horizontal slice. And we're going to see why a horizontal slice is going to be trouble. So if I make a vertical slice, we're going to slice parallel to the axis of rotation. So we're slicing delta x. Once we decided to slice parallel to the axis of rotation, so we chose to slice parallel to the axis. We can just immediately write down our volume of the slice. Volume of the slice will be 2 pi times the radius times the height times the delta variable, which in this case is delta x. Now all we have to do is go in and label the radius and label the height, then label x and y, and then write our definite integral. So we'll label the radius. The radius is always measured from the axis of rotation to the slice. And the height is always perpendicular to the radius. I forgot to label that this is the equation. This is the graph of y equals 6x minus x squared. Now I need to write r and h in terms of x. So I need to label where x and y are. So I'll pick the point where the slice intersects the graph. And so I can identify y, and I can identify x. So now it looks like r is just x plus this extra 1. So r is equal to, so I'll take the right end, which is at x, and I'll subtract the left end, which is at -1. So I'll have x minus a -1, or x plus 1. It looks like the height is equal to y, but that's no good. I need the height in terms of x. Fortunately for our heroes, we know that y is equal to 6x minus x squared. So now I have the radius and the height of the cylindrical shell in terms of x. So I can write the volume of the slice is 2 pi times the radius, x plus 1, times the height, which is 6x minus x squared, times the thickness of the wall, which is delta x. All of this we accomplish by not even worrying about what the final shape is going to look like. It looks kind of like a parabolic bundt cake. So here's like the hole in the middle of the cake. Here's the cake shape, but it's a very mathematical bundt cake. It's a parabola in cross section. And it's also fluorescent yellow now. So it's nuclear yellow cake. Forget yellow. Isn't there like a type of uranium, like yellow cake uranium? Well, this is yellow bundt cake uranium. So it's more presentable for parties. So we've got the volume of the slice. We form the Riemann sum. Our poor Riemann sum gets annoyed because we ignore it and we just go directly to the definite integral. We're like, oh, get out the way, Riemann. We want to go directly to the integral without passing go or collecting $200, even though collecting $200 would be kind of nice. I'm going to factor out the 2 pi. We're going to integrate this expression. I'm not even going to bother simplifying the expression. My algebra class is like, oh man, why I got to do is like that. The discrete delta x becomes a continuous dx, and we evaluate where x, the values, we find the values of x for which there's a slice. And the slices go from x equals 0 to x equals 6. Normally, in our definite integrals, we don't write x equals. We're told to write x equals because of the dx. But we really want to reinforce that fact because we're new at this whole writing definite integrals business. Even though it's a parabola, I'm so committed to the idea of not multiplying it out, I'm just going to appeal to my calculating machine to evaluate the integral for me. So x plus 1 times 6x minus x squared with respect to x from 0 to 6. So it gives us a 904.78, we'll call it. As usual, I'm just asking for an approximation to 5 significant figures. But it looks like it is 288 pi. So there's our exact answer. And here's our approximation. I think it's entirely appropriate to abbreviate the word approximation because it is just writing an approximation. I don't think I've written the full word approximation for a very long time. So we know what the volume of our uranium bundt cake is, but finding the volume of the bundt cake was not the point. Looking at the region and imagining it getting rotated around an axis and doing the analytic geometry, that was the point of the problem. So let's see why I like this problem so much that we're going to do it again. We said at the top that you could slice parallel or perpendicular, and that is your choice. But sometimes those choices make things kind of difficult on you. So let's do the same region about the same axis. But this time, let's slice perpendicular. to the axis. All right, so then have our parabola. Still going to go from 0 to 6. Still going to rotate it around the line x equals -1. All right. And this is still y equals 6x minus x squared. Let's now instead choose to slice perpendicular to the axis of rotation. So we'll notice that the axis of rotation is not a boundary of this region. So axis is not boundary. That tells us that the volume of the slice that we should use is pi times the big radius squared minus the little radius squared times the delta variable, which is going to be a delta y. Because our axis is vertical, so our slices are going to involve y. So now what we need to do is go in and label the big R and the little r. So the little r is the distance from the axis of rotation to the near end of the slice. And big R is the distance from the axis of rotation to the far end of the slice. That was way too high. Now what we need to do is label X and Y, because we know we're going to have to turn these horizontal R's, write these horizontal R's in terms of the vertical variable X and a vertical variable Y. So I'm going to have to label X and Y on my graph. So I'm going to look at the point where the graph the slice intersects the graph, and I look at this value Y, and now we run into a problem. This Y corresponds to two different X's. So that value of Y corresponds to two different X's. So this is a problem because the function y equals 6x minus x squared is not invertible on the interval from 0 to 6. It's easy to write big R and little r in terms of x1 and x2, but the problem is that there are two of them. So big R, I've been writing little r first, I think. Little r is the distance between x1 and the axis of rotation. So little r is x1 minus a negative x1, minus a negative 1. So little r is x1 plus 1, and big R is x2 plus 1. So we have two different values of x because the function 6x minus x squared is not invertible on the interval from 0 to 6. So we're going to note 6x minus x squared is not invertible on the interval from 0 to 6. All right. What we will notice, though, is that we're dealing with a parabola, and so we're still going to have to rewrite this in terms of x. This is a squared function, so our inverse is going to be a square root function, but the x appears in too many places. So we're going to have to do a little bit of algebra to solve for x. And of course, we're going to run out of space because I drew this one too big. So let's do a little algebra. We're still going to do the same thing that we always do. It's just going to be a little bit more involved because our function isn't invertible. In true math fashion, we're still going to try to invert it anyway. So we still need to write y equals 6x minus x squared as x equals, and there needs to be 2 of them. We need 2 expressions for the x. So notice that y equals 6x minus x squared is a parabola. And we're going to use the fact that y equals 6x minus x squared is a parabola to write 6x minus x squared in its vertex form. So notice that the vertex must be at 3, and then we'll plug in 3 to find out. So 6x minus x squared is a parabola. The vertex will be halfway between the x-intercepts. So the vertex is at x equals 3. And so if we plug that in, 6 times 3 minus 3 squared, we find that the y-coordinate of the vertex is at 9. So I can rewrite the expression y equals 6x minus x squared. I can rewrite this as a minus 1 times x minus 3 squared plus 9. So I rewrite the parabola in vertex form. The reason that we want the vertex form is that the variable x only appears once. And so now if I want to solve for x, I have y equals minus and x minus 3 squared plus 9. I can subtract 9. I can divide by negative 1. I can square roots, and here's where the 2 solutions show up. When we're solving and we take a square root of both sides, we get a plus or a minus. And then now here are our 2 values of x. 3 plus or minus the square root of 9 minus y. So in the middle is the 3. Then on one side is 3 plus the square root of 9 minus y, and on the other side will be 3 minus the square root of 9 minus y. So there's the 3, and then the plus and minus is evenly spacing a quantity about the 3. So we got 3 in the middle. And then we got some on the right. We got the same distance on the left and right. So back on our parabola, our slice cut into 2 x values. Here's x1, and here's x2. In the middle of the x1 and x2 is 3. And so it looks like x2 is going to be 3 plus the square root of 9 minus y, and x1 will be 3 minus the square root of 9 minus y. Because x2 is bigger than 3 and x1 is less than 3. And the vertex 3, 9 is in the middle. So here we have in the middle 3, and then we have plus the square root of 9 minus y and minus the square root of 9 minus y. So we're just utilizing the symmetry of the parabola to get our 2 different values of x. So finally, our volume of the slice was pi times big R squared minus little r squared times delta y. Big R, little r was x1 plus 1. And then I can write x1 as 3 minus the square root of 9 minus y. And then we have the plus 1. Then the big R will be x2 plus 1. And I'll write big R as, or x2 as 3 plus the square root of 9 minus y plus 1. So now the volume of the slice is pi times big R squared. So I'm going to combine the 3 and the 1 and write this as 4 plus the square root of 9 minus y squared minus little r squared, which I'm going to once again write as 4, but minus the square root of 9 minus y squared, all times the delta variable, delta y. Then we add up all the slices into a Riemann sum. But more importantly, we turn everything into a definite integral where the v total I'm going to factor pi out of the integral. And I'm going to regret writing this all over again. That's not that bad. And all the usual stuff happens. I just take my volume of the slice, I put it into a definite integral. My discrete delta y becomes a continuous dy. Got to remember I'm integrating over y this time. So I need y equals. I need all the slices where, all the y values where there was a slice. Now we're going from bottom to top, so we're integrating y equals 0 to the top where y equals 9. And then we find out if I've made a mistake somewhere. So I math a second pi, and I math 9. So I need 4 plus the square root of 9 minus y. Close the square root, close the sum and square it, and then subtract the next square. 4 minus the square root of 9 minus y. Close the square root, close the sum, and then square it with respect to y from 0 to 9. Hey, it worked. It's amazing. So we get 904.78. So this was just finding the same volume with a different slicing strategy. It involved a little bit more work because the function that we had was not invertible on the interval in question. But that's okay, we just had to work around the non-invertible parts. And also, fortunately for our heroes, it just broke down into a simple plus or minus because we stopped with quadratic. Any questions? For a more fun version of this problem, it replaced the 6x minus x squared with sine of x. And you have to do the same thing. You have to figure out where the middle is and then figure out how to express the plus or minus parts.
So how do we know when to use like a vertical slice and a horizontal slice?
You don't know, you decide.
Okay.
It opens up with a choice. You choose, in this case, we chose to slice perpendicular to the axis of rotation. Whereas in the previous way we did the problem, we chose to slice parallel to the axis of rotation.
Got it.
So that's the good news. You don't have to know. Any other questions? All right. This was certainly fun. It brought back some nice memories of algebra with this plus or minus stuff. Notice that we could also write things in vertex form by completing the square. But since it's very clear where the vertex is going to be, let's just go directly to the vertex form and use that. We could have also written the vertex form and found expressions for x1 and x2 with the quadratic formula, but that would be embarrassing because the quadratic formula is trash. And that's not how we should do things. We should use the fact that the quadratic functions look like parabolas and have all this symmetry. It's what annoys me about the quadratic formula in the way that we usually use it. It puts all over 2a and ignores all this cool symmetry. Mostly it ignores the cool symmetry because we don't recognize that we can use the distributive property on the quadratic formula. But all those things combine together to make the quadratic formula kind of trash. So anyway, that's going to do it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing.